Hi! Today we're going to be learning about how to construct a confidence interval. Let's say we have a problem like this. Suppose from a random sample of 500 people, you find that 300 of them get soda after requesting a cup of water. Construct a 95% confidence interval of the true proportion of people who get soda after requesting water. So before we get started, let's figure out what we're doing here. So basically, we have a sample, and from this sample we have the proportion that we find, or p hat, which is our sample proportion of 300 over 500, or 0.6. And we want to use this 0.6 value to figure out a confidence interval of the true proportion of people who get soda after requesting water. So what does this mean? Well, this means, in this case, that we would be 95% confident that the true proportion of people who get soda after requesting water falls within our confidence interval. It also means that 95% of the time, when we take a random sample, we're going to get a value within our confidence interval. Or, that also means that 5% of the time, we're going to get a p hat, or sample proportion, that is outside our confidence interval. Okay, so let's get started. How do we do this? Well, before we even think about constructing a confidence interval, we have to first see if this meets the requirements or conditions. The first one is randomness. The second one is independence. And the third one is normality. Okay, so in order to be able to construct a confidence interval, the sample has to be random. All the samples, all the samples have to be independent, and this has to be normal. So the sampling distribution, or the sample distribution, has to be normal. So how do we figure this out? Well, randomness is almost always stated. So if we look in the problem, we see that we have a random sample. So yes, we have randomness. How do we check independence? Well, independence is checked through the 10% rule. The 10% rule, let's write this down, 10%. The 10% rule states that if 500 is less than or equal to 10% of the total population, then this is independent. Or if you're selecting with replacement, then it's going to be independent. However, here we can see that we're selecting without replacement because we're not going to replace the people, or we're not going to ask the people who we already asked before. So this is going to be sampling without replacement, which means that we have to follow the 10% condition, or 10% rule. So what this means is if 500 people is less than the total population, or the total number of people who request a cup of water, then each trial is independent. Okay, so we know that 500 for sure is going to be less than 10% of the people who request a cup of water. That's just common sense. So we can state that, but in this case, because we're a little limited on space, we'll just put a check mark. And then normality. So because we're dealing with proportions here, we have to use the large counts condition. Or the LCC, so large counts condition. What does that state? Well, that states that, and I'm going to erase this soon, it states that P, or in this case P hat, times N must be greater than 10, greater than or equal to 10, and 1 minus P hat times N must be greater than or equal to 10. Now in some cases, in some very special cases, or when they tell you in the problem, it can be lower than or greater than 10. But in general, it's going to be 10. So let's do this. Now when we look at the large counts condition, we don't actually have to solve for both of, or we don't actually have to solve both of these. We can just say is p hat smaller or is 1 minus p hat smaller? So here, 300 out of 500 gives us a p hat value of 0.6. So we have p hat is 0.6, and 1 minus p hat would be 0.4. Because 1 minus p hat, which is 0.4, is smaller than 0.6, then we just have to do this. We just have to make sure that this is correct, because we know that this will be larger than this value here. Or you can just do both. So 0.6 times our sample size of 500, which is n. So 0.6 of 500 is clearly over 10. That's 300. So we know that this is a normal curve. Okay, so our normality is checked. And you have to show this, you have to show your work for the large counts conditions and explain the 10% rule or condition when you show independence. Okay, so because we're limited on space once again, I'm going to erase this. But take a moment to write these 3 conditions down. Okay, so now we have to construct the confidence interval. How do we do that? Well, the formula for constructing a confidence interval is COI, let's say that's confidence interval, is equal to statistic plus or minus Z star times the standard error, or standard deviation. Okay, so we have this rule. So what is our statistic going to be? Well, the statistic is the value that we find. So it's going to be p hat. Our standard deviation. How are we going to find our standard deviation? Well, this would be the standard deviation of our sampling distribution. We know that for proportions, the formula for finding this standard deviation would be p hat times 1 minus p hat all over n. Okay, now what is z star? Well, z star is the value that we find, or the value that we use when we construct a confidence interval. It's on table B of the AP Statistics formula sheet, and basically it just corresponds with your confidence levels. So, for 90% confidence, it's going to be 1.64. For a 95% confidence, it's going to be 1.96. And for a 99% confidence, it's going to be 2.58. So these are 3 of the more common confidence intervals. So it's good to have these 3 memorized because these are the ones that are most common or most often show up. Now, if we look at these, we can also notice something different. We know that 95% of the values fall within 2 standard deviations from the mean. So these somewhat align up with the standard deviation these somewhat line up with the z value, or you can find it on the z table. These somewhat line up with the number of standard deviations away they are from the mean, like when they correspond to the areas under the curve. But this is found in the formula sheet. And these 3 are the most common, so it's best to have these memorized. Okay, so now I'm going to have to erase these, and then we can actually get to the problem. So, the best way to start off one of these problems is just to label, or just to put down whatever you have. So you have p hat is equal to 0.6. We know that. Now we know our confidence interval C, or confidence level C, is 95%. Which means that our Z star is 1.96. Our standard deviation would be 0.6 times 0.4 or 1 minus 0.6, over 500. So now we're set. We just got to plug it into our formula. The confidence interval is 0.6 plus or minus 1.96 times the square root of 0.6 times 0.4 or 0.24 times 0.24 over 500. Okay, so let's plug this into a calculator. Well, because it's a confidence interval, we can either write it as from some value to some value because it's an interval, or for the sake of simplicity in this problem, we can just leave it with a plus or minus. So our final confidence interval is going to be 0.6 plus or minus. Now let's put this into our calculator. So we get 1.96 times the square root of 0.24 divided by 500, which gives us plus or minus 0.04 approximately. So our confidence interval is 0.6 plus or minus 0.04. So now let's put this in context. So in context, we would say we are 95% confident that the true proportion of people who get soda after requesting water is 0.6 plus or minus 0.04. So that's how you would express this in context, or provide a proper answer. Today we learned about constructing a confidence interval. Thank you for watching this video.